Good morning, California. Good afternoon, London, and good evening, Beijing. My name is Yiming Dai, an analyst in BAAI Community, and it's my honor to host this workshop today. In today's event, we have invited 6 scientists to discuss the origin and nature of intelligence. These 6 scientists are Professor Ma, University of California, Berkeley; Professor Doris Tsao, University of California, Berkeley; Professor Karl Friston, University College London; Professor Michael Wooldridge, University of Oxford; Mr. Jeff Hawkins, Numenta; and Professor Tiejun Huang, Peking University, and the Beijing Academy of Artificial Intelligence. In the first session, Professor Ma will give us an introductory talk about his recently published article named On the Principles of Parsimony and Self-Consistency for the Emergence of Intelligence, co-authored with Professor Tsao and Harry Sham. Professor Ma, the time is yours.
All right, let me share my screen. Yeah. First, thanks Beijing Artificial Intelligence Institute for the invitation. Let me share my screen. You can see my screen?
Yes.
All right, good. Let me put in full mode. So it may take a couple of seconds. Are you able to see my slides now?
Yes, it's very clear.
Okay, good. So as you see, right, this talk is trying to talk about the 2 things, on the parsimony and the self-consistency related to intelligence, right? So I think this was inspired by a whole bunch of talks with Doris, with Yang Kun. I mean, we were actually writing some proposals, and we're trying to identify this exciting development in the past 10 years, right? The artificial intelligence. Why it's successful and what it's lacking, and since it has drawn a lot of interest in related to natural intelligence, right? So one thing we identified is that despite this marvelous engineering advance, right, almost actually all the practice of artificial intelligence right now, based on deep learning or methods related, belongs to category what we categorize probably just called assisted intelligence. Meaning that everything the machine does is a human will transfer our intelligence to the machine, right? From the data preparation, from the design of a network, from the optimization strategy, even how well the machine did, the evaluation is done by human assessment, right? Machine very much has has no intelligence itself, right? A lot of the characteristics we know of, like human or animals and so on, primates and so on. So this has inspired, what we're trying to look for, what's missing. How can what are the necessary mechanisms would allow an intelligent being, either it's animal or a machine of the future, right, be able to acquire knowledge, develop intelligence automatically. So that's really what the also, there's a tremendous of literature right now, right, about artificial intelligence. Very, very, mind-boggling, right? So many different things. Maybe this is a time to try to make things a little bit simpler, right? As Einstein says, everything should be made as simple as possible, but not any simpler. As I read, the recent book by Jeff, right? Really marvelous thing. I think one thing capture. It's the idea of the nature does something very simple, very unifying, right? I think that's something in the faith we have, right, in science and also in engineering as well. Just trying to get the. So how do we start with something very, very simple, right? Let's start with very, very simple. Try to, the past 10 years we have accumulated a tremendous amount of inductive research about AI, right? All kinds of engineering, but can we do something slightly deductive? From some simple and fine assumptions and principles, can we actually understand things better, unify things better? Right? Of course, many of the things are pieces people probably already know, but there's a way to assemble them. I think it's interesting, providing some interesting perspective, unifying perspective. Hopefully it's useful. See, this talk will be mostly about a computational mechanism, right? I'm not an expert in natural science or natural intelligence, but this is how we look at it from a computational scientist, data scientist point of view. What a machine should be doing, right? So we start with the high-dimensional data, right? Videos, images, audios. Our human brain are bombarded with tremendous amount of high-dimensional data, right? We try to make sense of it. Right. So that, for us data scientists, we think about our data, despite many, many different categories, right? Thousands of categories. Right? Each category may be just one image would be a point in a million dimensions, right? In a million pixels, right? But they have very, very good structures, right? Images associated with apples lies on very low dimensional spaces. A moving pencil, right? A million pixel is actually probably traced out one dimensional curve, right? So those are the structures we're trying to learn. Now the question is, despite all this data, what do we try to make sense of it? What is a common goal? Either engineering-wise or scientific-wise, right? So one thing we started thinking about it, maybe that the learning is actually have a very, very unifying goal. It's just trying to seek a most compact and structured representation of the data. That's it. But we'll be more specific, of course. And that actually very much also capture what has happened, right? Since it's called the deep learning revolution, right? In a nutshell, what really deep learning did is saying that if I have thousands of categories, cropped images, right? I can try to learn a mapping from those data points to their labels, right? One-hot labels. This is one way of organizing the data, right? And of course, this mapping can be very complicated, and we model them with the deep networks, mostly as a black box. Still, right, people don't really understand what it's doing now, but yet with a careful chosen, tested, tried network, this feeding seems to work okay, right? You try to minimize, basically try to enforce the output of the network, f of x, right, match with the labels, the one-hot labels, right? So there's a correlation between the labels and the logics of the network outputs, maximally correlated. This is called coarse entropy. This actually generated a tremendous success, right? Also revived the interest in both deep networks as well as interest in intelligence. Of course, engineering-wise, right? This kind of system people have started to understand more now, and you sort of get what you reward, right? You ask the network to output the prediction like this, and indeed the network tends to learn, right? To map the features, sort of, this notion of neural crabs, map to this one-hot labels. This is called. And then here is a question. Even this actually gave me a very good classifier, but this doesn't necessarily explain why I called apple an apple. It's a taste, it's a color, it's a shape, right? What really the network has learned, it gets buried in this black box. And also, just knowing something is an apple does not necessarily means, right, you will be able to regenerate an apple, right? What if I ask you to draw an apple, to do a generative task rather than just classification? Now let's just try to generalize this a little bit, right? If we want to preserve, if we shifted the attention away from the labels rather than towards the data, we try to capture the distribution of the data. How can I map if my data lies on the multiple mixture of distributions, or in fact, every distribution in high-dimensional data, they're degenerate? I mean, it's better categorized as we call a manifold, right? Much higher, lower dimensional manifolds. Then what do we mean by that, right? So naturally, we want to establish a mapping such that the output of the network, right, is highly structured and organized, right? For example, if the manifold associated with the apple is 5-dimensional, we may want to map it to a 5-dimensional linear subspaces. And also apple and oranges are very different, hence we may map them to incoherent or statistically independent models, right? Orthogonal subspaces or independent Gaussians. Hence this actually leads to the question that maybe what we're trying to do is just to try to map such a mixture of submanifolds to a mixture of subspaces, incoherent subspaces. And we call this kind of model as a linear discriminative representation. It's both discriminative and also generative. And how do you know this mapping is faithful? Which means that we're not mapping 5-dimensional apple to 6-dimension or 4-dimension. We're not losing anything. We're not over-representing anything. So mathematically, naturally, you want this mapping to be 1-1 and also reversible. Hence, there must exist a generator going from the notion of apple back to the original image. Right? Hence, it's F and G, encoding and decoding. The question is, how do we learn this? Right? What deep learning has anything to do with this? One thing, if this is our target, if we agree for a moment, right, this is what we want. We want to transfer our data to this kind of standard object, highly low dimensional and orthogonal. Then how do we measure that? How do we know we're doing a good job, right? So there's a very natural, of course, right? The practice deep learning gives people information we can grab whatever loss function there is, right? What is the most objective, right? Actually, information theory has provided a very good answer to that. Right? If this is a family of models you want, then the difference between the rate distortion, how many bits I need to encode such a representation, give me a sense of the measure of goodness of the representation, the quality of the representation, right? The difference between the rate distortion, how many bits I encode the whole versus the parts, we call it rate reduction in rate distortion. It's really just measures the information gain by representing data lies on subspaces, right? So we prefer, for example, the representation in the left to the right. Why? Because that maximizes the information gain, right? The difference between the whole and the parts is maximized. And it is all captured by sphere packing or packing in personal balls. Right? It's a very basic quantity and nothing heuristic about it. Hence, naturally, that if we seek a good representation, we really should maximize this rate reduction. That will push our representation into the configuration of the left. Why this is important? This unifies everything people have done so far with deep networks, right? So, for example, how do I optimize this quantity? Obviously, this is it looks like a sophisticated expression, right? But it turns out very interesting. This is a closed form. Actually, write down this in closed form. Now, optimizing this closed form expression, of course, it's hard to find a global optimal, but turns out there's a universal method. We do this. Maybe that's what the nature does. Is that if it's a complicated problem, at least I can try gradient descent, right? I can optimize this object incrementally by taking the gradient descent direction. Now, as soon as you do that, if you calculate the gradient of this rate distortion function, and you get expression of this. And there's multiple interpretations, endless interpretations. You can think about this as a linear operator acting on your features, current features. Then that naturally leads to a residual network. Or if you do up to, do the Taylor expansion of this inverse, if you don't like it, you get exactly the operator of the transformer per layer. People call them attention head. Well, it's kind of a joke, right? Kind of joking around, right? Machine learning is really the art of giving different names to the same thing. To me, they're all gradient of compression, right? The rate distortion. The measure that measures the volume of my data in high dimensional spaces. So this is sort of show this thing. So this is actually, if you do this, and since there's multiple classes, you naturally get a parallel columns. That's actually what we call it, right? Multi-head attention, right? ResNext are exactly, or mixture of experts are precisely emulating this kind of architecture. Now, turns out this is very interesting, right? So since the inception, artificial neural networks for 70 years history has always been practiced following the left column, right? Has always tried to fit input-output relationships. I mean, the architecture has always been trial and error. Tested. So 30, 40 years, right? People try different things and try to fit. And it started with random initialization. The people still debate what the operator should be. And through backpropagation, very enforceful, right? Very brute force. And by the end of the day, even you train a very good function, and it remains a black box. What is the internal representation? People still don't know. Right? And then actually, now from this compression point of view, right? This information theoretic approach, and everything is almost upside down now, right? The object function is absolute white box. and nothing for human to choose. It's completely objective. And the network per layer is precisely conducting incremental greedy descent. And the network is forward constructed. You don't need random initialization, right? Of course, you can fine tune it to use backpropagation. By the end of the day, the network is a white box. And also the representation you learn internally is also a white box. Now the question I mentioned internally, right? So this is sort of one-way street, right? We map the data to a family of subspaces. But how do we know this model is faithful? We didn't lose anything, right? This is a one-way measure feature. There's no guarantee that if you just do this one dimension. How do we know that there exists inverse map G can map the feature Z back to X with some faithfulness, right? This is really said, this is actually autoencoding, notion of the autoencoding since the early 1990s. People have been solving this. Now, of course, you can emulate it. We all know the solution if the structure is linear, right? It's called a PCA. But if the structure is manifolds, it's much more complicated, especially if it's the manifolds of images. We don't really know what is even the distance between two images that makes them similar or not similar, right? Hence all the story about GANs, try to measure this distance, right? The difficulty is really how to measure in the high dimensional data space, very sophisticated structure. How do I compare the distributions if they're not as simple as subspaces, right? It turns out, well, if your structures are subspaces or Gaussians, the distance is closed form, right? By the way, almost all the distance you heard in the literature, right, from a computational point of view, like KL divergence, mutual information, maximum likelihood, right, Jensen-Shannon, W distance, nothing is tractable. They're not tractable to compute, right? And then all the things you see in the literature, they're just approximation, various heuristic approximation of those distances. Now, the question is, nature is not aware of those things, right? What they might be minimizing, what the nature should know. So it turns out if your target is very sparse, low-dimensional linear structure representation, then the measure can be closed form, right? Just given by the rate reduction. It's extremely efficient to compute. But there's one big question though. If the subspace are my, the representation I'm seeking internally, but what is the distance in the data space outside, right? In the 3D. How did the nature learn that, right? At least even computationally. And this actually comes to a very big question is that, do we even need to measure in the data space? Nature never does that, right? We never carry a ruler to measure, oh, my estimate of size of the table or cup is right or wrong. Kids never learn that way. Right? We never measure errors in the world. But how do we learn a faithful representation of the world? So it turns out, is it possible to learn everything, measure everything only in the feature spaces? Right? And this actually turns out it's very simple. This is another thing we actually draw inspiration from nature, right? In nature, everything is closed loop. That actually inspired the entire field called control theory, right? So in order to say if I'm actually prediction of the world is faithful or not, right? The measured error in the data space is extremely difficult, computationally intractable, if not impossible. Right? So now, then there's a very clever way to do that. You don't measure distance in the data spaces. You map what you regenerated, your prediction back to your in your internal representation, measure the difference of the joint representation of what you really see and what you have remembered, predicted. Right? This is essentially you close the loop and minimize the error in the feature spaces. Right? So in order to minimize this difference between X and the estimated X, you minimize their difference between their features. Bring everything back to a closed loop. Now, is that enough? If I control my generator from my internal representation, I imagine, so that my feature, the sensor, my visual pathway can no longer tell this difference. Is this enough? Actually, it turns out that's not enough. Why? Because F is actually usually very compressive. You try to draw low-dimensional structures. It kills a lot of spaces. Right? In order for the Z to be faithful, the X and X hat, there's no differences. You have to proactively adjust F to detect if anything is missing. Is there still something different between X and X hat? So basically, after G minimizes the error, F has to take over to check, to interrogate, self-interrogate, self-critique if there's still something I missed. So that makes this kind of a sequential game between the encoder and decoder. Right. So in the end, put it together, right? F is encoding from the outside data, and the Z gets the representation. In order to check that, G is a decoder, right? And they form a closed loop control system, right? And what is the target? The target control is actually controlling the distribution, right? The generated distribution needs to chase the real distribution of the data, right? Hence, in game theoretical terminology, it's called a pursue evasion game, right? G is trying to chase, make sure the blue curve chase the black curve. F is trying to separate them apart, right? If there's any difference, F is trying to amplify them. They together play this game, and the solution is actually the fixed point of this loop. It's exactly the equilibrium point of this game. Hence, you can write down everything as a minimax game. Of course, the terms are exactly measuring the distance between the subspaces. That shows in the picture here, right? The distance between those subspaces. Therefore, you end up with a minimax game. There's nothing for human to decide, for you to choose, right? It's an information theoretical measure, measuring the configuration in terms of internal representation, and everything is closed form. And it's in a closed form, and you are learning something completely explicit in your discriminating representations. Nothing for you to decide, right? Then suddenly you realize you don't need to specify any prior or surrogate of the target distribution. You don't need to measure anything in the external data spaces. You don't need to approximate any distances, right? Kel divergence, Janssen, Shannon, W, they're all gone. And those heuristics, regularization terms, does it work? Yes, it actually works even better, right? So it actually not only can learn a generative discriminative representation, and the learned representation is structured. It's not hidden. And also suddenly, all the things with the learning generative model, there's neural collapse, neural mode collapse, those phenomena disappeared. This closed loop system is very sturdy, very stable. And also you can learn in a supervised way if you know the class label, such as ImageNet, or you can learn in a completely unsupervised, continuous way. The loops never forgets, right? So remember all the open loop you train neural networks, right? People say this is the catastrophic forgetting. Basically, you try to train the same network for learning new classes, new tasks. All the information about the old classes start to forget immediately almost, right? But for it's a closed loop, things can be continuous, can be. So in summary, right? So this really is a sort of this kind of closed loop transcription, what we call it, right? Transcribe high dimensional data to something highly low dimensional structured. Right? It's really like a sort of universal learning machine, right? From our brain, body to even, RNA to DNA. Right? Transcribe something, organize something, right? And also even the simple loop really have different pieces come together naturally, right? For example, the segments F and G are really, the neural networks are really play the role as the latest way to realize an optimization algorithm. What is optimizing? At precisely some information theoretical quantity, the coding, right? The most compact codes for the data. And what is the mechanism to ensure you actually learned correctly, right? You need to use a feedback loop so that you actually can measure everything internally. You don't have to do anything externally. And this game mechanism is to ensure that There's no differences with real observations or their internal representation. Right? And the whole process is a white box. Right? You don't decide anything. Right? The objectives, the network architectures, and learned representations. Nothing for you to guess. Right? And there's actually opened a lot of things. Right? There's tremendous empirical evidences right now. It works very, very well. But our understanding mathematically has been very limited. Right? What is the nature of this game, when they converge, and how do we control the linearization of the manifolds, and so on and so forth. What is the optimal density distribution after you optimize this kind of codes, right? Why there's this kind of, closed loop can automatically conduct model selection, doesn't overfit, doesn't underfit. And naturally, probably for this panel, right? So there's some question really is that what is the connection to the natural intelligence? So far, all I've said is that really from a mathematical computation perspective, right? Unifying things a little bit. Then is this similar thing, similar mechanism, similar principle has been, emulated or in the nature, right? In particular, right? So at least this kind of view start to question a few things, right? It's really advocate, right? Something much more natural. Right, you can construct networks without random guess, but in a forward construction fashion rather than learn from backward. And this really suggests we should do everything in closed loop, not open loop segments. Just like people have learned in control 70 years ago, right? From nature, open loop control is expensive, non-adaptive, unrobust. We're repeating that mistakes after 70, 80 years, right? And also, we've also realized closed loop is not just enough to make the learning autonomous. You need to have self-critiquing or self-interrogating mechanism, like a game, right? Of course, there's also advocated by people like Judy or Pearl, right? And the self-interrogating, self-critiquing mechanism is necessary to learn things such as causal relationships. Everything I said today is about learning the distribution, right? Does not capture additional logical causal relationships. Yet, even for those things, you need a self-critiquing mechanism. The most practice of artificial intelligence right now has none of this. Right? So another thing is that transforming signals to structural representation is very important, in my view, to go into the next steps, right? That needs to make it possible for us to do higher level, making representation symbolic and semantic. To put things together, right? This is my view of what is deep network. Deep neural networks are just nature's optimization algorithm. Nature doesn't have MATLAB. Nature doesn't have PyTorch. It has to realize optimization layer by layer. Each layer is realizing one iteration to maximize the gain from the input to output. The gain is precisely measured by the information gain. Now, just have such a optimization algorithm is not enough. With just one segment, we need to build systems, circuit that are autonomous, right? Can learn things autonomously without the supervision. Right? Therefore, the closed loop transcription has all the mechanism are the basic learning units for autonomous self to check the learned models representation are faithful. Hence, using error feedback, using self-critic mechanism. And this is not enough. Hoping that you have one big gigantic network, you lump everything into that. That's the current practice. People call them foundational model. In my view, that's completely wrong. Okay. You cannot do that. Even from a computational point of view, to learn a classifier for thousands of classes or tens of thousands of classes, it's incredibly challenging, okay, the optimization. But what if I break them down? I solve hundreds of smaller classifications, right? So I can use, if this kind of mechanism works, I can treat it as a building block. Each one probably just pay attention to dozens of classes. A different cognitive scale, time, spatial scale, right? I power them up even for different senses, I repeat, do the same thing. As long as I make sure every loop, every unit maximize information gain or optimize information gain. I gain something out of that. Right? I can transfer continuous unorganized continuous signals to organized structures. From then on, we can bind them based on statistical association, or we can ground them based on one-shot supervision. Right? So organize this further to form high-level concepts or semantics. Right? Why you do this? In fact, this parallel, I mean, of course, Jeff's book has characterized, much better than I did, is that there's other benefits associated with this, right? So you can think about, this transcription distill important information. But for important information, you need to protect it. I think the one way to protect it, make it robust to noise, corruption, is precisely you do parallel distributed representations, right? So I just wanted to summarize, right? Many things here, the pieces we already have. I mean, what we try to do is that to piece things together a little bit. In fact, many of the ideas are now new, right? You can trace back the book of cybernetics by Norbert Wiener, published in 1948. He already touched upon almost all the elements. And his intention is precisely investigate what are the mechanisms to have machine to emulate the kind of learning mechanism of animals. Autonomous learning, not assisted intelligence, right? So there's maybe not the coincidence that, after all this year, we start to identify the same thing, right? But probably in a better form, how those pieces fit together into a purely computable, measurable fashion, right? And this is, again, following this paper. In fact, our recent position paper is based on a series of technical papers on the read reduction, for example, how to measure the objective, and how to use closed loop framework to learn it correctly, right? Yeah, that's all, right? In the end, right, we really try to say that this is just our, sort of very from a computational side to understand what have people done in the artificial side. And we find that there might be some higher level governing principles that can provide very plausible explanation for all the networks people have been playing with. And also to suggest ways to really assemble them in a highly integrated fashion to build systems are capable of, basically white box systems, capable of, to acquire knowledge or acquire information automatically, and maybe form the basis for higher level intelligence. That's all. Thanks.
Thank you, Professor Ma. This is a very profound talk. I think we can move on to the panel discussion session right now. First, we will let our guests to discuss some common issues raised by Professor Ma's introductory talk. And we will move on to those questions that we collected just before this event. And at the end of panel discussion, if time permits, we will let audiences to raise their hands and ask questions directly to our guests. I think our guests can speak freely right now.
Okay, well, I can go first as Mike Wooldridge if nobody else wants to jump in. So thank you for the fascinating presentation. Interesting to see issues that I have intuition about that you're making quite precise, I think, in the presentation. This is not an area that I'm a specialist in. I'm from a different area of artificial intelligence, but have a very strong interest in the principles of artificial intelligence. And I think it's the principles of AI that your talk is appealing to. And what's intriguing to me is that I think what we've made, what the community has made over the last 10 years is tremendous progress in what you might call architectures for machine learning in particular. And, we've seen that an awful lot. I mean, I think your talk explained that beautifully. And where that's led to, you mentioned very briefly, the thing of the moment is foundation models, large language models, the diffusion models that we're seeing that are creating incredible images. And these are genuinely impressive achievements. But I think they are a sort of, a consequence of these improvements in architectures for machine learning. I think we've seen much less progress in architectures for artificial intelligence, which is, I think, not quite the same thing. And I think you were hinting at that. I think you didn't use quite those terms, but I think you were hinting at that. And what I mean by that is, what large language models can do, what these diffusion models can do. It's tremendously interesting, but it's not the same as artificial intelligence, not yet anyway. And I think there's an awful lot missing from the bigger picture of AI that actually I don't think we've really begun to explore at all. So, for example, for me, I mean, I think it's useful to keep reminding ourselves, we are great apes. We're monkeys with a sense of entitlement, as I sometimes put it. And we exist in a physical world, the physical world of planet Earth, between roughly sea level and about sort of 10,000, 15,000 feet above sea level. And what Mother Nature has engineered through a very lengthy process, billions of years long, of evolution, is when we're born, is an artifact which is capable, which is engineered to be able to learn to operate in that environment, so the physical world of planet Earth, but also an artifact which is engineered to be able to interact with other monkeys with a sense of entitlement, with other great apes. So the social aspects of, of artificial intelligence. And I think those two bits of the puzzle we haven't yet seen. I mean, I see, this tremendous progress, and I don't wish to diminish it at all, the tremendous progress that we've seen, which is very real and genuinely exciting. But these are like subroutines that I would expect a true artificial intelligence system to use. They're components of intelligence, but they're not the big picture of artificial intelligence. So that was a rambling statement, but I wonder I'm curious how other people respond to that and what your responses are.
I completely agree. What we discover are segments, as I said, right? And for control, I have a control series, right? So what really ran out the big models and also feeding data, right? Even the diffusion models and so on and so forth are really just segments. They're precisely open loop control, right? It's not like it doesn't work. In fact, this control started with that. We try to train open loop systems to invert the system so that we can control them. It's not working. Control people know that, but it's expensive, right? You need a lot of input of the data to identify system, and also don't expect it to be adaptive. Don't expect it to be robust. People learned that lesson about 100 years ago, but in the past 10 years, we forgot all that. Okay, this is another thing. And also, you talk about the diffusion model. And nature not just do one thing. I think nature is much clever, right? So in fact, the rate reduction is exactly everything in the past 10 years people do with the high dimensional data. They are basically measuring the volume, right? They're not doing anything different than this, right? So even in the rate reduction, you can see there are two terms. One is about expansion. For different things, we expand them. That's exactly what we call the diffusion, expansion, or contrasting, right? People like to use different words. They're all exactly the same thing. Now, but for data that are similar, what do? We don't diffuse them. We compress them. We denoise them. We actually contract them. So basically, I mean, this picture just shows you that the manipulating the data distribution, there's both diffusion and denoising. You choose the data spaces that people are, what you should do is simultaneous. You should not just do diffusion. Yet diffusion only allows you to get hold of the distribution, but does not allow you to organize the distribution. You can sample it, but you don't understand it. You're not organized in a way you can use it very easily for inference. Precisely connects to what you just said. The learning is not just get hold of the distribution, learning is also about organized distribution, right? So you organize in sparse, compact way so that you have a basis. Once you have those structures, subspaces, those neurons, each cluster of neurons representing each subspace, structure representation, then you have a basis, at least to me, at least computationally, to start to form discrete random variables, discrete notions such as objects, semantics. But I'm not an expert on that, right? I don't know what it would take to get on the symbolic representation or language or even logic or even causal. But at least from a signal or data analysis point of view, we have provided a basis for that. Without that, if all the distribution is still hidden in the feature spaces, you don't even have computational basis for that, for those higher level notions. At least this kind of transcription provides an interface for that, right? Interface between the external world and your internal representation. And hence you can probably do higher level inferences.
If I can, I'll jump into this conversation as well. Again, thanks for your talk, Yi. That was great. And Michael, I think at least some of us agree that the distinction you made very clear here is that the difference between machine learning and intelligent machines, for many of us, is pretty clear, and I would agree with you on that. I think, you know, we all, I think, would also agree that machine learning and brains learn some sort of model of the data that they get. And of course, the model they learn is going to be very dependent on what data they're trained on. To me, one of the biggest distinctions, and I don't think you addressed this, Professor Ma, is we know that brains are sensory motor systems. We don't observe the world as images. We interact with the world, moving with our bodies, our hands, our eyes constantly. This is not some sort of uncomfortable artifact we have to get rid of. This is how the brains work. And so if we really want to capture intelligence, I believe you have to understand how brains learn models from sensory motor input, that the brain is constantly being fed information about how its sensors are moving through the world. And we do know from neuroscience now that the great deal of the neural machinery in our heads, whether it's in the neocortex or in the hippocampal complex and other places, is dedicated to processing movement, positions, orientation, poses, locations. It's a very complex model of a structured model based on movement. And so, you know, maybe the algorithms you talked about are great, but I think until we actually incorporate this idea that we learn through movement, we learn a structured model, and we learn how things behave when we interact with them, whether that's people or cars or phones or whatever, we won't begin to capture what intelligence actually is. And I'm proposing that one distinction where we have to think about sensory motor inputs is perhaps the most important one to move us past where we are today.
Absolutely. What I said today is mostly a framework to more abstract data, right? I hear what you just said. You know, in the data X, in fact, you can easily incorporate the spatial dimensions such as the space and time. So this is just to try to capture what's in those correlations, right?
Yeah, right. I'm agreeing with you. I'm not saying it wouldn't work. I'm just saying until you incorporate that stuff, it's it won't be intelligent.
Yeah, we have seen precisely. Yeah, exactly. I read your work. You made a great point there. So we have to see. We have actually witnessed that this kind of framework start to really works very, very well, and we have some recent work precisely on all this, right? So you actually can this give you like hand, right? So now you don't need robotics, right? We still don't understand our hand, how delicate our hand coordination. Turns out that you actually can do this precisely in this this is our latest work. We start to get the benefits of this kind of framework now. Really a closed loop compressive framework. You can actually train the hand. Everything shows up automatically. Even the gate, you can train on just one object. Turn on your hand, just one object. Sitting object on simulation. You don't need any other things. You actually can the real robots that can rotate many different hundreds of different objects, and the gate of you handling the objects emerge automatically. The pace and adapt automatically. through this kind of, it can actually encode all this sensing about the weight, shape, and even friction of the object. Gets encoded in this loop, gets learned. Of course, there's still things we don't understand, but this is exactly what you're saying. You actually can incorporate this temporal pattern, temporal interaction with the world, and can learn this automatically. And
one of the interesting debates I've had with between AI and neuroscientists is, in the brain, it's clear that there are prior assumptions about the world in terms of its structure, in terms of that there are neural structures that literally represent reference frames and assume that knowledge is going to be stored in a certain sort of format. And most deep learning systems don't have that. And the question is, do you have to have that embedded? And brains do. That's not a debate.
Yes.
You're born with this knowledge. This is assumption about the world. Your brains are not tabula rasas. They're like, the world's going to have a certain type of structure. We're going to figure out the details of it. And that's an interesting debate in AI, whether you have to incorporate that or not. I've had to talk to some deep learning people say, well, our systems must be figuring that out. They must be creating reference frames because they can do it. They work so well, as opposed to building AI systems where you a priori make those assumptions about the nature of the world. I just throw that out as a sort of high-level conversation points here.
Yes, from engineering point of view, right? We see space and time very special. In fact, in all the systems that just showed you robotics, right? We encode those explicitly. But I'm just curious, right? There's still debate that those things can be acquired through learning, through just observation, observing videos, or observing, interacting with the world, right? The spatial temporal interaction. Can that kind of representation be learned automatically, or is something already we may be selected through nature, right? We get hard coded somewhere.
Well, that was the debate. That was the debate I was just talking about, right?
Yes, exactly.
My belief is that that if you just hope it gets learned, it may get learned, it may not get, but there are real advantages to making some a priori assumptions about the structure of the data in terms of how quickly it learns, the type of representation you have. Clearly, that's the way brains work, and whether we have to replicate that or not is a debate. I'm on the side of, hey, don't throw away nature until you really understand it. Just those. I'm like, I don't need to worry about those details because, as we all know, the brain is the only example we have of it.
What engineers are good at, we bypass, right? Whatever we don't understand, we try to bypass or wrap into a black box.
We all do that. Everyone does that, right? We can't understand everything all at once, so we pick the things we think are important.
Great discussion, Jeff. As a primate neurophysiologist, I might push back a little bit on your statement that's very clear that there's so many priors that brains encode. I mean, I think it's clear that, all brains, baby brains look very similar. There are definitely anatomical constraints, but what those are actually encoding, I think is completely unclear. For example.
Yeah, go ahead, sorry.
Okay, and for example, like humans all end up with a visual word form area, and that is not, genetically encoded, and it arises due to experience. And so there's just a lot of questions there. I mean, certainly a lot is encoded. We don't know how much or what exactly that is.
I'm speaking of sort of lower level things. For example, one of the things we've postulated is, one of the most exciting areas in neuroscience, as you know, are the encodings in the hippocampal complex, such as the grid cells in the medial horizontal cortex. And that's a sort of a general method for doing path integration and structured learning. And we said, hey, we think this is probably happening throughout the cortex. And now we're finding that. Neuroscientists are finding these grid cells, which are kind of reference frames. They're very specific for learning certain types of knowledge. And we're finding them everywhere from the primary sensory regions to high level, regions in the cortex. And I think they're going to be found everywhere. So when I say there's prior assumptions, it's not about what they're going to represent. It's just that the world is going to have structure of a certain type of structure. And that's the kind of thing I'm talking about. Like there's an assumption that knowledge is going to be stored in reference frames and there's going to be movement associated with it, not like what the knowledge will be. So maybe, I don't know if you still disagree with that. But to the extent that we find that those neural structures do exist throughout the neocortex, which is the organ of intelligence, that is the kind of prior I was talking about.
Mm-hmm. Yes, I actually, to just follow quickly on Jeff's comment, I actually even believe that right now, I have worked on computer vision all my life, right? we have always envisioned, we always try to do, in our paper, we also mentioned that a little bit, in 3D vision. And this is also Harry Shang, we had a lot of discussion. He's a graphics guy, right? We start to realize, right? So computer vision has always working, try to learn from images to 3D. And graphics is going backwards, right? We're going to segments. But it turns out we actually start to believe that maybe the 3D representation, just like Jeff, you were saying, right? The reference, also the orientation and the shapes, might be just the most compact representation. It's our brain's way to compress things. Rather than, it's something 2D has to break down to pieces. So this is something we actually start to believe that, this is from all the visual inputs, and this kind of spatially coherent 3D representation, even temporally coherent representation, is the ultimate compression. That how we organize our sensory inputs, right? It's actually something internal. So of course it's reflected reality, but it's something our brain is able to achieve, right? Representing internally. There must be mechanism. Our representation internally must be able to represent those spatial and also temporal relationships precisely the way it is. So that's how we start to see that. We're sort of even in the process of trying to realize this.
Yeah.
Can I ask Karl a question? Because I'm very curious what you think. I mean, Karl, you've advanced this idea of the Bayesian brain and predictive coding. And so I'm very curious about your reaction to Yi's talk, and specifically, I think one big difference between the framework that Yi proposes for imposing self-consistency and the traditional, round-Ballard notion of predictive coding is that Yi proposes that the error is measured internally at the very highest stage, rather than having a hierarchy of prediction error neurons, across the entire brain. And I apologize if this is getting in the weeds, but I'm very interested in your thoughts about, what can we say about where error is measured, right? I think most of us would agree there probably needs to be some kind of closed loop in order to do unsupervised learning of the world, but what is the exact form? And I feel like this question of where is error measured is a really critical one.
Yeah, no, that's not in the weeds. That's, I think, an excellent question, which was playing on my mind, particularly in relation to Yi's question about, is this biologically plausible, and what evidence, anatomical and physiological, do we have that this kind of message passing or learning occurs in cortical hierarchy? So I think it's a great question. Just standing back, I just want to congratulate Yi on the talk. It was a wonderful talk, starting and ending with two of my favorite catchphrases, keep everything as simple as possible, no simpler, and that which I cannot create, I do not understand. I think that both of those speak in a sense to the world model. I mean, I call that a generative model. And the generative model has to be as simple as possible in accord with Occam's principle. I think that encapsulates for me a number. So two of the very important things that this view brings to the table. I mean, there are lots of things in terms of being asked to talk about common ground here. There are lots of themes you've introduced, but it seems to me that compression, in the service of and in the spirit of minimizing complexity and keeping things as simple as possible, is a central theme here, just at an abstract level. And in that spirit, I'm wondering whether it would be useful to use those underlying themes and principles to connect this scheme to other schemes, and in particular things like predictive coding, exactly to answer Doris's question. I can see a number of ways of doing it. I was trying to sort of simulate the equations as they went past, and I failed to completely link it formally to an inference or a Bayesian perspective, or indeed predictive coding. But I think it would be a great game to do. So places you might want to start, for example, I just go back to the notion of compression and link that to the notion of minimum description length and minimum message length and algorithmic complexity formulations of intelligence and universal computation, someone of induction, for example. There may be a fundamental, foundational link there that you can exploit. In terms of predictive coding read as Kalman filtering, I think there's a very, very clear link. So I'm trying to work towards implementations or formulations of this kind of scheme in terms of predictive coding. And if I read predictive coding as effectively a variational Kalman filter, where technically the prediction errors are the variational free energy gradients that you do your gradient descent on, which might be one metaphor for neuronal dynamics, then I think there's another really nice link there. And I mean that in the sense that the variational approximation to the model evidence, or the log marginal likelihood, known as, say, an evidence lower bound in variational autoencoders, that log marginal likelihood or variational free energy can always be expressed or decomposes into accuracy minus complexity. So it seems to me that the complexity term holds exactly this imperative for compressibility and finding the simplest, most parsimonious explanation. And I am hoping that your expressions can be rewritten in terms of complexity. In Bayes and in Kalman filtering and in sort of formal implementations of predictive coding, that complexity is a KL divergence between the posterior and the prior. So your representations or beliefs about Z, the latent states, before and after, and then you basically score the information gain as this complexity term, which is the degree to which you change your mind on the basis of this new sensory evidence or these new outcomes. So if that's true, then I think there may be a formal link between the scheme that you've described here, the closed loop rate reduction, rate distortion approach that has this, I think, quite crucial dialectic in it. And the dialectic I'm talking about is exactly the keep it simple, but no simpler. Another instance of this is James's maximum entry principle, which is another instance of this kind of optimization, but it's maximizing the entropy, the volumes that you are speaking to with the spheres versus the ellipsoids in coding under constraints. So there's always, if you like, another side to the coin here. One expression of that is the dialectic between accuracy and complexity. And from the point of view of predictive coding, that often sort of creeps in at various levels. And just returning to Doris's question then, I mean, if you just look at the way that predictive coding works, it is extremely similar to this, the final image you showed, where you have this sort of state space architecture feeding into a discrete, yes, precisely. So you've implicitly got a sort of hierarchical scheme here. And by hybrid, I mean a mixed continuous and discrete state space representation. The continuous one would be, in my world, implemented with predictive coding, and the discrete one with some equivalent kind of variational message passing or belief propagation. Both of them can be, I think, articulated in using the language that you're using. The difference would be, though, that in predictive coding, certainly of the kind that people posit for neuronal hierarchies, it's a sort of local energy-based minimization. So you're minimizing prediction errors both at the bottom in terms of the both the x's and the top in terms of the z's. So you get this dialectic, or one kind of expression of this dialectic is in terms of the prediction errors being minimized throughout the hierarchy. And that's the kind of thing that's missing in backpropagation. And I think that what you're bringing to the table here moves us on in virtue of the fact you've now got this this closed loop architecture. But I'm struggling to see whether there is actually a formal connection with predictive coding, given that I would expect to see the prediction errors being minimized both at the bottom and the top of this hierarchy. And in a sense, this speaks to Jeff's observations about, there are implicit structural priors there, and they are, one can regard the role of those priors as in defining the space in which the very high level prediction errors are being minimized. Do you have any insights that I don't on this?
Yeah. May I? So just to connect, I'm not already sort of expert on all the neuroscience predictive coding, but let me just from a computational point of view to address what also Doris said, and also there are two things people tend to make, not necessarily mistakes. I mean, at least you don't understand computationally. Also, I think Karl sort of suggests that where is at the bottom or the top. So people tend to think either I'm doing in the bottom on the X space. That's exactly to my point of view. That's actually what GAN people made a mistake, right? We try to directly measure distance at the distribution of the data space, which is at the bottom, which is intractable, which is, if not impossible. Of course, people approximate thousands of papers, right? KL divergence, those are degenerate distributions, high dimensional spaces, even computing the distance, W distance, Jensen-Shannon distances, they are not computable, period, okay? Yes, you can keep writing another 10,000 papers, how to approximate them, sample them, right? Using thousands of GPUs, that has been doing that. This is one way. You don't do at the bottom of X, right? Nature doesn't do that. Okay, the question is, do we do everything in the very end of the Z? Not necessarily. The reason diffusion model works so well is, by the way, that's old. The diffusion model learned distributions is at least 300 years old idea, right? Trace back to Laplace. See, people say, oh, we can actually, since I have computers, I can sample X, I can minimize the distance. Don't do that. 3,000 years ago, right? 300 years ago, Laplace says, no, you don't, you do greedy descent. Langevin discovered this in physics, right? It's called the Langevin dynamics, right? So you do greedy descent on the log likelihood, and that converges to the Gibbs distribution. Now, about the predictive, if you don't do the bottom, you also should not do at the very end, Doris. What you should do is make sure your deformation, every step you are doing the coding decoding, every increment is forward and backward. Just like diffusion model is doing, Langevin dynamics suggesting, you diffuse, you denoise. You deform, you undeform. You remember both paths. You do this predictive coding locally. Every layer, you could do that. So although I draw the closed loop as F and G, right? In fact, in this schematic image, you can think about even this, each layer is a small loop, pushing the data, pushing the distribution in one direction, diffuse, denoise, and also undo that. Remember what you did to your data. Remember what you did, where you come from. You can have this loop, in abstract loop, actually implemented in a layer by layer fashion. So hence the predictive loop could have had all the stages of your process. Just remember that, right? Form a sort of a reversible chain. That's also possible. Basically, this notion of loop is actually, it's just abstract, right? But the implementation can be many, many, many different ways. So also that said, the second thing related to what Karl was saying, absolutely, right? So the whole idea of redistortion actually comes from it precisely try to describe all the complexity associated with the coding decoding, right? The minimal description length, both the codes of the data distribution as well as the code book. Actually, this is actually some of the whole work traced back to some early papers we did actually many years ago, precisely trying to do minimal description length. to make maximum likelihood, make all this computable, actually, for high dimensional data, for data that has the degenerate distributions even, right? So that's actually said, I mean, indeed, even if you look at the form of, that's why this form is very, how do I say this? It's very universal, right? So you can say this is actually just computing. You can think about it, looks like this. This is actually exactly the auto-regression of data, or auto-regressed by other data points, right? So exactly what's the behind ideas, behind common filters, behind the estimation. Only that after you compute this gradient of how your volume deform locally, you decide what to do. You decide to diffuse or decide to denoise, decide to expand or decide to compress, right? So that the ideas of filtering or common filtering and so on are precisely buried here. This is exactly, you can think about it, this is almost has a Wiener filter flavor in it, right? Precisely doing linear regression locally. And leads to also no surprise, right? People that practice the 5-6 years of auto, they believe they can use in random search, neural architecture search, right? Auto ML, try to search architecture. Turns out that there's only a couple left, survived. Residual networks, transformers. Those happen to precisely emulating the gradient of this local autoregression. And you use that measure to decide what do you do to the data. And you do that in a potentially auto-encoding fashion, probably every layer. Not wait until the end, not try to go back to the X, not wait until the very end. You do that incrementally. I think that's actually, I learned one thing from Jeff's book is that if the literature learns something that worked, right? All you have to do is just repeat it, copy it. You just do this layer by layer and also or column by column. And everything is very unified and it doesn't think too much. It doesn't know too much. And just knowing this works and then doing things in that fashion. It does unifies a lot of things that way. Yeah, this is exactly literature's way doing common filter or doing Wiener filter almost, right? So.
Can I just bring this discussion to closure then? So that's a very clear answer, and I think sort of it allows one to definitively answer Doris's question. So if you are allowing now for a hierarchical composition of this locally closed loop belief updating through the mechanics you've described, then I think this is exactly consistent with predictive coding, and there's an enormous amount of evidence for this kind of hierarchical, replicated, canonical microcircuit. I'm thinking here of 1,000 brains sort of formulation, but in this sort of abstract sense, exactly in the way that you express that there's a common calculus that has a physical neurobiological substrate that is replicated in a hierarchy. And I think that the kind of structural prize that Jeff was talking about in terms of grid cells and frames of reference, I think one important structural prior that we inherit from evolution is just this hierarchical structure within which your closed loops can play out in this sort of consistent, simplifying, compressing way. So I would say that this probably is very consistent with a certain level of analysis with one's understanding of computational architectures in cortical hierarchies and subcortical hierarchies.
Yes, and also I had a discussion with Yana Kuhn. I mean that just purely from computational side, right? We are dealing with extremely high dimensional data, and like images or audios and so on. And this kind of the only measure you can hope tractable, or you can hope to compute are the volumetric measures, such as exactly the covariances, the second order statistics, or right? The local unnormalized likelihood. That's exactly all this diffusion model, transformers, residual networks, everybody's doing, right? Although they call different names, but they're exactly the same nature mathematically, computing the local shapes or correlations among the data. And that also leads to, turns out actually, maybe, nature, I'm not an expert, but I'm just guessing, some of the Herbian architecture learning, right? Precisely, it's just through the correlations. And that's only things, even computer, that's something we can do. We can compute reliably or efficiently. Anything beyond that, second order or higher order, almost forget about it, right? Even modern computers, we can, in the curvature of the manifolds, forget about it, right? Haitians of the object function, forget about it, right? Nobody's can implement them. And even you have the super computers. So in that sense, right, the computability also sort of coincides maybe what nature learns to do, right? Those are the things you can reliably, efficiently compute, relies on the correlations of the data. And hence you build your knowledge around that way, you distill information in that way.
Could I pick up on one of Jeff's points in relation to that? You've emphasized a lot the dealing with very high dimensional big data. Mm-hmm. One way of, if you like, accommodating Jeff's point about the fact that real intelligent artifacts move and thereby are in charge of the data that they sample means that the big data perspective may not be necessarily the most apt to understand real intelligence, in the sense that it may be more like smart data. So take, for example, the difference between the amount of Shannon information in a high resolution RGB image and the data that the human eye samples, which is actually very, very restricted and carefully chosen with saccadic eye movements. So this notion that you need a sense-making machine that can handle very high dimensional data may be slightly misguided, because biological artifacts carefully choose the sparse data, the smart data that will maximally, in your language, I would imagine, speak to the information gain. You could also articulate that in terms of Bayesian surprise in the visual search literature, the resolution of uncertainty, intrinsic motivation in robotics. All these, as you so fluently expressed, are just words, different words for exactly the same mathematical quantity that underwrites this sort of closed loop compression.
Yeah. So
I like that. I like the idea, the way you expressed that, Karl. I've never thought about it that way, as sort of getting rid of this high dimensionality, but I think that's right. I mean, when we look at the world, we don't see images, as you pointed out. We see various sort of subsets, and we move around. We don't move around randomly. We don't learn what an object looks like by presenting the eye with a picture. We learn by attending to different components and seeing where they are relative to each other. The same is true for touch. We have to take our fingers, or a single finger or multiple fingers, and move them over an object. It doesn't mean all the data we get is useful. Sometimes we get information that's not useful. If I'm scanning your face, my eyes might go off to some, your ear, and maybe that's not very useful at this point in time. But it does learn to say what are the interesting, or the most what are the most poignant pieces of information I can extract from this world through movement. I like the way I'm just saying I like the way you phrased that. I would agree with it 100%. And it's I think it's a key part of how we deal with the complexity of the world. It's not just about labeling images, it's about understanding the entire complexity of our surroundings as we move about the world. It's like extremely complex environment, and we can only learn it through sampling. And we only learn a model of a subset of it, because we can't sample all of it.
Yes. So this is actually absolutely, so Karl, just clarify, right? So I'm exactly opposite to advocating big data, right? So this is actually the whole book we actually wrote recently is exactly from the perspective of the data are high dimensional, but the structure extremely low dimensional. And precisely mathematically, we need to understand what is the minimum sampling complexity, right? That's hence the notion of compressive sensing. right? The sample's complexity should be proportional to intrinsic degree of freedom of the data distribution, not, right? The more the better, the larger better. Only that you have a brute force method, you need more and more data. You know, nature is very clever. Actually, also even mathematics are very clever, right? You have to, in this book, it's precisely capturing if you're, at least if your data is a piecewise linear structure, local low dimensional subspace structure, we actually can characterize the mathematical limit, the tight limit. How many samples do you need? Turns out that's very, very few, extremely few. That is called compressive sensing. You can do way beyond, you know, what the engineer previously believed was a liquid sampling theorem and so on and so forth, right? So this is actually the essence of it. Precisely understand the structure of the data. And I think nature explored that so that we do clever sampling, compressive sampling sensing for that purpose, to get those structures and consistently and most efficiently. Yeah.
But the question here is can it be done without movement, without subsampling the world, right? That's I think the question is, you know, I would argue it's absolutely essential. It's not a matter of taking this massive data and reducing it to the simplest form possible. It's starting off with saying, let's not take the massive data. Let's selectively
That's the
sample.
million-dollar question, right? So far, all the mathematics so far is about a very generic low-dimensional model, linear ones. But what you said, is absolutely important. The our value functions we're sensing is a function of time and space. They have very special structures. What are the best sensing strategy? I don't think people know. I mean, a lot mathematically, right? There's a lot of empirical people do that. You know, even engineers, people do different ways to sample, you know, visual data, sample temporal data. But there's really no mathematics, especially with nonlinearity, right? If you look at the Robert Werner was the inventor of linear systems control, right? But in this book, 1948, he already moved on. He actually said to understand brain, you need to understand nonlinear harmonic analysis, right? Although the mathematics was in infancy, but he already realized that how to sense, right, nonlinear structures in space and time is something we have to have breakthrough in order to understand how brain works.
Well,
right?
you know,
I don't think today we have any answer, a clear mathematical answer to that.
I think we have part of the answer to that, and I'm not claiming I haven't read Wiener's work in a long time. So, but part of the answer to that is, as I mentioned earlier, the brain makes assumptions about the underlying structure of the data. So imagine you have some sort of reference frame that's if you're trying to learn the structure of an object, like a smartphone or something like that. You have a reference frame for that. The brain establishes a reference frame, and so information can be assigned to that reference frame, and that's a very efficient and a coding scheme. And it also allows you to sample data and build models of objects, which you then forget components of it. You know, the first time I experience something, I might notice all these details, and I might temporarily remember that, but I can forget it. But the structure stays. Some of the details stay the same. So it's a once you've assigned observations to some sort of structured reference frame, it becomes the task of what's important, what's not important. It's much easier because you don't have to remember all the details. Some people will know more details about an object than other people, but there's at least a way of deciding, like, here's some information. Where do I put it? How do I store it? I can store it relative to this reference frame, and maybe I'll forget it later, or maybe I won't. But there's at least there's a knowledge, like I can sample the object and know where to put the data in a sort of an efficient way. I don't have to discover sort of the underlying structure of you know, the world is sometimes three-dimensional, and we deal with that, you know, 4 dimensions of time. So I'm just pointing out that by pairing it with some assumptions about the structure of the data, the process of which deciding what to sample becomes much easier. You can even oversample, and it doesn't cause problems. You just don't remember it all.
Jeff, I mean, I completely agree. I mean, in fact, this is $1 million question in you know, all these people are like playing with the transformers for visual data, right? We were doing position embedding. Even the latest work, Hinton has been working on the whole part hierarchy. Precisely, I spent a lot of part of my life doing face, you know, alignment, shape. Precisely, you know, the engineering we're doing our own way of, you know, brute forcely try to representing those relative spatial frame relationships. we really can learn from each other, right? I really think this is one problem needs a lot of unification. In fact, the proposal that Doris we just put together with Yang Kong, this is the first theme. How do we encode those spatial, relative spatial temporal relationships?
Right. Okay, if I could bring the conversation up another high level again here, I think we're all trying to achieve the same thing, right? We're all trying to get to some end goal about a learning system with sufficient representations of the world. Maybe some of us will agree or feel more strongly about the idea of sampling through movement. But we're all trying to get to the same point. My approach is I like to study the brain, right? It may not be the best solution. Doris is asking me about that. It may not be the best solution, but it's a good one. It works. Maybe we can do better. Maybe engineers and mathematicians come up with better methods, but maybe they'll miss something that we learn from brains. So yes. I think the goal here, we are not adversaries in this task. We are all trying to get to the same end point. I believe that there is a solution that we'll all be happy with sometime in the future. And we each bring different things to the party. I've been sort of, for many years, I felt that the neuroscience end of things has been underrepresented in the world of AI. Maybe it's my personal bias, but it felt like that.
It has to, right? Because the engineering that's doing brute force thing doesn't mean that they're really doing the right ideas, right? I mean,
but you know, some of the nicest ideas, you know, when I first started in this field many years ago, one of the AI scientists said to me, "Well, the brain's just a messy machine. Why study it? It's just a mess." And you know, so it was like, well, maybe it's something we can learn from it. So it doesn't mean that, again, the brain is the ideal solution, but it certainly has got some tricks that we can all learn from. So I just want to just make sure there's a lot of people listening to this conversation that we should all be hopefully agreeing that we're all trying to achieve the same result. And we're just coming at it from different directions, and that's where we bang and argue with each other about these things. But
exactly. Everybody, we have different pieces, right? It's really about how to coexist. I mean, be able to unify them. And in fact, even after all these years, right? People do this, that yes, the deep networks see success with the classification images, but that's only the object gets cropped, centered, right? Prepared for the machine to learn. But he has spent his last several years just trying to understand what if that's not the case. Right, you have to understand parts or the whole different location alignment. This is also age-old question. Also has a lot of interaction with neuroscience, right? How do we segment images? How do we co-segment images? And also co-concurrence, right? This is 30 years of history. I mean, 30, 40 years even computer vision. And people know, I mean, there's many proposals. A lot are actually inspired by some early, neuroscience.
Yeah, I think a lot of some of the stuff was inspired by early neuroscience. I think in fact, most of it is. I think the question is, there's been a lot of advances in neuroscience in the last 20 years, and that hasn't really infiltrated. It has, like, I mean, there are AI researchers who pay attention to this. I'm not saying there's no one does, but I think it's more can be done.
Yes,
and incorporating it, even fundamental things about how information is represented. We know that in brains, information is represented in sparse codes, very sparse coding. That's how information is represented. There are no numerical values in the brain, right? It's almost all sparse coding, sparse representations, distributed representations, place codes, and so on. And that's a whole other area that we generally isn't discussed at all. But does AI have to move in that direction completely? Where today's AI neural networks are really based on very high numerical accuracy, which is biologically not the way it works.
Engineer, we like to get the low-hanging fruits first, right? Or in a brute force way. I mean, we don't necessarily. That's always the case. And then, but after that low-hanging fruits are gone, we sort of really force ourselves to address some of the problem. I think recently you'll see increasingly people start to get to revisit problems such as the image segmentation, co-segmentation, concurrence, and so on and so forth, right? Which that the computer vision started with, right? So this is actually always, unfortunately, it's always the cycle of engineering communities that everybody just rush out to get the lower hanging things rather than the right things, right?
Right, and we all also want to go for the most elegant solution, right? That goes back to the Einstein quote in some ways. Nature doesn't always follow that rule, right? Nature, you look at the biochemistry and DNA, it's a mess. There's all kinds of crap going on inside of that, and and that's true of nervous systems too, right? There's all a bunch of redundancies and weird stuff going on in there. So we want to like jump to the most beautiful, simple, elegant solution. I do this all the time. And half the time I'm wrong when I do it. I say, oh, that's got to be the way these are going to run through this because it's so elegant, right? And then, that's not the way it works. So I think there's this, the yin yang between the elegance of theory, whether it's biological theory or whether it's mathematical theory, and then there's the reality of the real world, and that we're going to end up somewhere in between those two. It's not one or the other. Exactly.
That's why I think that you're absolutely right? So even that I think this is kind of the kind of why we can learn autonomously. This must be a very robust mechanism that, see, we get through our brain. I mean, the animal can, in a different environment, we learn different things, right? So meaning that we need to have this kind of system needs to be fairly sort of adaptive to what it's exposed to. This kind of adaptivity is very, very important. What we're trying to say here is that precisely you should not just train your data, the system on the data, then deploy it. No, the system should have the ability to actually handle this kind of uncertainty in the world, right? Build that capability inside, so that we can make even find what's likely, what's plausible, rather than always making just single-minded deterministic predictions. Right? Unfortunately, many of the current system is still designed for that, for engineer. And the really don't have this kind of mechanism, allows you to really adapt. I'm actually also a big fan. I read a lot of paper from Karl Friston about the brain's the Bayesian machine. Indeed, we rely on our past to make prediction and inferences, but also in this experience, I actually believe that probably our brain should have a mechanism is also adaptive Bayesian, meaning that while we're using the prior, we're also shaping the prior, right? And we actually can adapt, change. If I live from cities to a desert, right, my experience will change, gradually adapt to things, right? My knowledge can also change. So this should have this kind of adaptive Bayesian framework, right? Constantly play self-critic your model against the reality and make changes to that.
Right. That's clear. That's clear how we learn. Right. We learn because of predictive errors. It doesn't require. It's unsupervised. It's self-supervised. So I think we can all be in agreement on that. That's one of the great things, and Karl's really been a proponent of that. So, and I'm a fan of it too. So that's one of the big pieces of the puzzle, right? But it's only one of the pieces of the puzzle. So, but it's, I think one we can probably all agree is fundamental.
Yeah, could I come in at this point? It's fascinating hearing the conversation. I mean, I think a couple of points. I mean, I think, Jeff, just to the point that you made about, there's all sorts of weird stuff going on in human bodies. I mean, evolution has not ended. We are a work in progress, right? Every component of us. And it's not like we're some kind of platonic ideal organism, which is the ultimate thing that we should sort of aspire to. We are very much a work in progress. Exactly. That's exactly right. So I think that's one point. I think another point, I mean, a standard criticism that I hear from colleagues in the machine learning community, or a frustration that's very repeatedly expressed, is in the rush to get ahead in progress in machine learning, people use, I mean, in your phrase, the kind of the low-hanging fruit, but actually very often the low-hanging fruit is, just some quick hack to make things work. And maybe it does work, or it appears to work, but actually nobody really understands there's any deep reason for why this works, or what the principles are. So just some observations. But actually, my question to all of you, and I'm really intrigued to hear this. I mean, I think this is you're from a very different background to the background that I'm from. What do we need to make progress in AI? I mean, I think you've sketched out some principles there, which I think we all broadly agree with. But actually, do we just look to the brain, the nervous system, and the body? I mean, is that it? Is that what we need to make progress in AI? Large language models, GPT-3 and Palm and so on. These are all extremely cool toys, but they clearly aren't the end of the road for AI. But they're doing something interesting. What is the next steps? I mean, where should we be looking? I mean, is it, is Mother Nature going to give us all the clues we need and we just need to look there? Or, I mean, I'm very interested to hear, Karl, for example, what your views on that would be.
I think my views will probably be your views, and I suspect also Jeff's views. So I'll answer that. Returning to this question of actively engaging with the world, but also Yi's observation that that it is important, if not a solved problem, to know where to look for data. So I'm basically going to say the next generation of artificial intelligence will have an innate curiosity. Instead of answering questions, it will ask questions. It will be generally interested in you. So you'll have your Siri or your iPhone who will be quizzing you because it wants to know about you. And I think this is an example of acquiring smart data. So smart things so actively move to sample the world in a smart way. What is a smart way? Well, I think that's fairly simple. I think it connects very nicely to this notion of information gain. It's just basically the expected information gain I expect if I do that. And actually, you know, this has been a formalism and a calculus in statistics for over half a century, and originally devised by Dennis Lindley in statistics. And it's, you know, it comes under the rubric of optimal Bayesian experimental design. And I use that phrase, of course, because, again, speaking to one of Jeff's point about what we can inherit or what you can inherit from neuroscience and psychology, if you regard perception, active sensing, active sense making as hypothesis testing, then you need the principles of how you design your experiments. And those are just the principles of optimal Bayesian design, which is just being curious, which is just acting in a way to maximize my expected information gain. So I think it all fits together beautifully, to be quite honest. So I'd say curiosity.
Do you think the world is important?
I like that. One word, that's great.
Do you think the world is important, Karl? I mean, do you think actually disembodied AI is really a thing? I mean, I think that I'm a skeptic about that. I think the world is important. And I believe, you know, human intelligence is partly social. I mean, you know, we are, as I said, you know, we are all apes, and a big part of our intelligence, it seems to me, not least language, is about those kind of social aspects. I wonder whether others agree. Absolutely.
I mean, I think that was implicit in this sort of talking about things that move, that there is an embodied, there's a 4Es aspect to this. But I think you're taking that even further. So when I said curious about my world, what is my world made of? Other things like me. So I think that sort of social aspect, that multi-agent aspect, that co-construction aspect is absolutely essential to understand true intelligence. And you could even argue that in a world, if I have to build a world model or a generative model of a changing world full of imperfect, apes with entitlement, the curiosity that we're talking about is going to be lead to inference about the nature of you versus me, and could actually be a principal explanation for self-awareness, which I think may be another ingredient for true intelligence. But you only need that in the kind of world you're talking about, which is basically made by you and me.
Karl, that's incredibly reassuring to hear you say that, actually. That's
Karl, you just summarize everything in just one word. I mean, that's amazing. So, see, this is exactly also the phrase, right? I had some conversation on Twitter with Julia Pearl. I mean, he's the causality guy, right? I mean, the Turing Award winner. We have exchanged a lot of email recently. So it actually has precisely a lot to do with just what you just said, right? Here, this is the phrase. Even let's say, I don't know, you know, I'm a very, you know, naive engineer. We want to just get a distribution of the data. Just learn the distribution correlation. Just closed loop correct error is not enough. You need to be self-critic. Have I learned everything? You have to take active. So that's why we say that, right? The sensor itself has to move. F has to move to check if there's any difference I missed remains. Even currently, my control has minimized error. So in the traditional control setting, right? F is fixed. We only design controller to minimize error. Actually, that's not enough. You have to have the self-critic mechanism. F and G has to play a game to balance. So I was talking to Julia Pearl, why? Because probably he saw our paper. So he said that, well, you only learn distributions, you cannot learn for infer causal relationships. You know, you really have to interrogate, you have to intervene, design experiment to check, find out the relationships between the variables. So I was telling him, even forget about the causality, even to learn the correlation right, you need to be curious. You need to have a self-critical mechanism. Otherwise, you cannot know if you have learned internally are right or wrong. So that kind of mechanism, either in terms of self-critiquing, self-interrogating for causal, or the curiosity to explore the world, to check if your model is right, that has to be in any autonomous intelligence. Unless we do just current machine learning, right? Just human supervised all the way, from data to evaluation, right? It's just that machine. I mean, we're just emulating what we ask them to do. But any sort of autonomous system, without this kind of mechanism, is absolutely, you cannot make it autonomous. So that, I think the curiosity might be the word to sum of all, right? And I even tell Junior Pro that maybe discovering causality is an accident. Maybe the machine nature start with just to try to learn distribution. But because it has this self-critical mechanism, it's maybe the ability to discover the relationship between different structures, which is causing what? Through the same self-critic, self-interrogate mechanism, through this game of the internal with the world. This kind of game mechanism, right? That amazingly, even Nobel winner in his book, he actually mentioned this in his 1961 version. He actually added a chapter, precisely said, the learning mechanism is still a game, not just a closed loop. So actually very, very interesting that we somehow start to forget about that after so many years. Good.
Can I go back to
Yes, maybe I can give some comments from the AI researchers. Yes, more and more AI researchers working on the explainable, the white box, the mathematic foundation for the AI framework. Yes, that is a very promising and very important direction. So Professor Ma proposed an excellent framework for that. So that's great. But I want to see there are much more AI researchers work on the maybe black box, maybe gray box, but maybe larger and larger neural networks to generate stronger and stronger intelligence. So I believe that is the direction for AI. So for AI research, what our mission is to build a system with stronger and stronger intelligence. So that is, so the big model or the large scale neural networks, I believe, is a mainstream for many years. So that's my basic observation, or I believe that is a fact. So that is one observation for the AI community. So second is that is on the famous. So what I cannot create, I cannot understand. So my understanding for that is, firstly, we need to build a system. At this stage, this system may be black box, but if this system can work, can run, can generate some phenomenon, some intelligence, so that is first stage. The first means if it is a white box, that's good. But if there is a black box, it's still okay. So then after that, we can try to understand the principle, why the system can work well. So that's my understanding for famous. So for the neuroscience side, so I'm not a neuroscience scientist, but I want to say something for that. So I believe we are very far to the origin and the nature of the intelligence, to understand the nature of the intelligence. I believe the most important thing, just I mentioned, is that we need, firstly, to understand the structure of the bio-neural networks. I mean, the details, the structures of, so that when we know that, one can build artificial neural networks, something like, in detail, much similar to the bio-neural networks. So that is the first step to build stronger, intelligent system. But not the principle. I believe it's very difficult for neuroscientists to give AI researchers some principles to help us to build AI systems just based on several simple principles. What we can get from the neuroscience is the neural networks, the real neural networks that will help us to build much better artificial neural networks. And then we can train that kind of neural networks and we can generate stronger and stronger intelligence. So that is my vision for the next, for the future of the artificial intelligence. That's all. Thank you very much.
Thanks. I just want to jump into your question, Michael, as well. A very inspiring question. And so I'm a neuroscientist because I think the brain can help us to advance this understanding of intelligence. And specifically, I think the current advances in neural networks have been based on our understanding of early structure, visual cortex, and receptive fields, and so on. And I think the next big challenge for neuroscientists is to understand how you transform that ConvNet-like representation into a symbolic representation, right? I mean, several decades ago, Anne Treisman, psychologist, proposed this idea of object pointers. And there's this notion somehow that the brain has some kind of a graph-like symbolic representation where each object is represented by some kind of pointer and point to all the contents of that object. And we really have no idea how that's actually instantiated by neurons. And I think if we can really gain traction on that, like have very solid experimental understanding of how the living brains do that, solve that problem, I think that'll give the next generation of neural networks a solid foundation for reasoning about the world and building symbolic systems.
Could I comment upon that, Doris? Because I think it's a really excellent point. It also speaks to that final graph with that hybrid model, that mixture of continuous and discrete state space with symbolic representations. My comment is really a question. In a very, very simple sense, the very existence of things like classical receptive fields, or indeed extra classical receptive fields, and indeed place cells and grid cells, the kind of physiological architectures that Jeff was talking about in relation to reference frames, could not one interpret the very existence of a receptive field as somehow discretizing our representations of the brain in our brains, in the sense that you're tiling some sort of perceptual space with discrete, compact spheres, very much like the spheres in one of the graphics that Yi was showing us. Could it be that the very existence of receptive fields speaks at a quite simplistic but fundamental level to a kind of discretization? That this state of the world, for example, means that to a certain degree of certainty, talking about the messiness of neuronal systems, to a certain degree of certainty, this edge is moving at about 8 degrees per second, and not any other. If you just define a receptive field, is it not really a way of carving nature at its joints in terms of discrete tiled representations? And if so, I think that speaks to a really fundamental question about continuous versus discrete or symbolic representations in the kind of graph that we have at the bottom there. So what do you think about receptive fields?
Well, I don't think receptive fields carry a symbolic representation of the world. I think it's implementing that picture that we see on the screen right now. I mean, receptive field is just filtering the input, I think there's a confusion. I feel like there's confusion in your question between the hardware and the software. Like I feel like the question is how does the brain at the software level represent a graph and objects as discrete units? Whereas I feel like, are you talking about like a single neuron, because you have a single neuron that somehow makes it discrete. But I think like with single neurons, you can represent things in a continuous way. You can represent them in a discrete way. It's going to be done by collections of single neurons, that's for sure. So I don't think that the fact that a receptive field is represented by single neurons tells us much about. I mean, and we do understand completely, I think, what a V1 receptive field is doing. There's nothing mysterious, right? It's just taking a local average of the stimulus. It's not capable of representing, an object as a symbol.
But I think part of the question was discretization. Is that a word? And I think we'd have to say that any model in the brain has to be some sense built on discrete representations. I mean, the world, if a continuous world is infinite, and we can't deal with that. So I think it's a separate question whether it's symbolic, is whether it's that a method. And that's how I interpreted Karl's question. Maybe I got it wrong. About does that tell us something about how the models are just based on discrete entities? And I think that's true. If you look at classic receptive fields in V1, they don't represent all angles of orientation. They are just discretized. You can interpolate between them by a couple of columns being active. But I think that if that was Karl's comment, I think maybe perhaps there's some truth to that. But maybe I misinterpreted your question, Karl.
Oh no, I think that's and discretization was exactly that, and I'm talking at an abstract level. I take exactly what Doris says, but one could also look at this the discretization that you just mentioned as an apt explanation for the kind of messy encoding. If you can, I think there's something you talked about interpolation, and that in turn speaks to the degree of coarse graining, and that in turn speaks to the degree of compression. So I think there's space of representation in the discrete coarse-grained carving nature into little tiles or at its joints, which allows now for the notion that you can have the right coarse graining of your reference frames or your representations or your, which of course is something that can be optimized. Optimize in relation to compression or to this, the simplification. So I think this debate about discrete versus continuous is really fundamental, and I'm sure it's not resolved. I was just really asking, if we look at the brain, is there not a lot of evidence already for exactly the right kind of coarse graining in the service of a kind of dimension reduction?
Mm-hmm. Yeah, so just in this picture, right? So in fact, it's discrete or continuous may not necessarily in conflict of each other, right? So that the first stage, precisely maybe some of the transcription is trying to organize the continuous functions, continuous distributions to subspaces. Once you have those, each subspace can be represented by small number of bases. They can become considered, if subspace can representing one discrete concept, right? Meaning that that subspace may be just apple, and so on. And that actually start to serve as basis, right, for higher level abstraction. And those are much easier to summarize and so on. So this is basically this kind of structural representation providing a interface for this kind of a bridge between the continuous distribution and something can be easily discretized, and also keep the generality there as well. And for space and time, maybe that we don't need. We maybe just doing lossy coding, right? So that's actually the whole thing about the rate distortion is that it's just packed. You only remember things up to an epsilon ball, right? Any errors beneath that you ignore. That's the only way we can just store finite bits, all right? Anything continuous in a finite the storage space. But that doesn't mean that we're throwing away important things, right? So that's why the whole decoding is make sure subject to that precision. I constantly check my model if my prediction agree with the observation up to that level of precision. If not, I improve or allocate more resources to do that.
You know, you go back to Karl's question earlier about discrete and continuous. Here's an interesting observation from neuroscience. The main way people think about continuous representations in neuroscience is perhaps the rate coding of the firing of a neuron. You know, how fast is the neuron firing? There's a lot of evidence to suggest that that's not actually that important at all. For example, there are some very high-level cognitive abilities, quick image recognition and so on, where they've shown that the neurons involved don't have time to generate a second spike. That only one spike is sufficient, and therefore no rate coding is possible. And that tells you then it has to be a spatial code that's important there. We also now know that in many neural systems, the actual very precise timing of a spike relative to a background frequency is critical. And so again, that's a very discretized sort of representation. It's not like this idea that neurons are some variable number of spikes per second. That really, it doesn't seem to be holding up much at all. Yes, we do see neurons that do have increased rates of firing and so on. I'm not saying that doesn't exist, but the mechanisms we've actually learned about, they're much more precise than that, and they're much more discretized than that. And it has to do more with precise timing and spatial codes than it does with rates, and those are discretized inputs. So I'm just going back to that comment that some people still have this idea that neurons are just these like represent some sort of real number variable. In the vast majority of cases, that's not the case.
Okay, so in fact, I want to say this figure in effect is something like a cognitive framework. It's not neuroscience framework. So when we're talking about the neuroscience, I believe the neuron spiking, so the connection, so the circuits, so we are talking about that. But for this functional figure, I mean, so it's a cognitive science.
I'm a computer science or mathematics point of view, right? I like to think about, it might be beneficial sometimes we think about from a mathematical principles or from the deductive framework to understand things. I think the understanding, unifying things is not the purpose, but it's a stage to advance further, right? Summarize what we have done. I completely agree with Professor Huang. I mean, engineering, just like in science, experimental science usually needed a way, right? Discover phenomena, discover possibilities, but a theory or understanding comes after. And then you have theory for physics, theory for chemistry, and so on and so forth. But again, the theory helps to really summarize what has been done. And also,
this is a classic debate between theorists and experimentalists. You can see it in physics as well, right? The experimentalists dismiss the theorists, and the theorist says, "No, we figured this stuff out before you did." And I think the same thing's happening here. But I go back to Professor Wang's comments earlier. There are a growing number of senior AI people who've concluded that deep learning networks are not going to cut it, that we need new fundamental ways of going about this. And the list is quite long of those senior people who've said this. So I think you're in the majority position today on this. But I think it's many people, including myself, feel like, no, the deep learning networks are going to be limited. And I think theory can play a huge part in how to go forward. It's not like we just have to build it and figure out how it works. We can also deduce theoretical constraints and ideas and guide that. And in our world, we're deducing those are coming from the neuroscience, and you can deduce that from the neuroscience. I think people dismiss that, just don't know the neuroscience. So it's easy to dismiss something if you don't, it's complicated, it's hard to study. I know we're running out of time here, so I was trying to keep bumping up the conversation here. So the top level ideas that we've discussed. I think there is this big tension right now between some AI people thinking we can just run with deep learning networks forever or for a long period of time. And there's quite a few people think, no, that's not going to cut it. And we have to come up with other approaches. And that's maybe that's a background to this conversation today, perhaps.
Yeah, as I said earlier, right, from a high level, I mean, the current really training networks end to end, that's kind of exactly that's something that lesson control folks has learned, right? Also inspired from nature, that everything alive, everything precise or adaptive, robust is a closed loop, right? That's Wiener's contribution. I mean, he was a zoologist actually at Harvard, and combined with mathematics. So I think the principle does help disruptive things, help revolutionize things. Engineering, yes, we can make tremendous progress by holding on the current practice. I mean, just by having more resource, more computations. But we will advance. But nevertheless, right? It's ideas from nature, ideas understanding mathematical principles or scientific principles better. We can actually revolutionize our practices and get to the next level.
There are some audiences raises their hands. I think all our guests could spend some time answering their questions. I think Tiejun Zhao could speak right now.
Hello. Hi, Professor Ma. Yes.
Hi.
Hi, thanks for your awesome talk. I'm Tiejun Zhao from CHK, and my advisor is Professor Jia. And I'm really inspired by your talk. And I want to ask one question or one dilemma. I think there are more and more engineers in the field of computer vision, and there are fewer and fewer researchers like you that can consider some first principles or some theories of computer vision. So I think there are many reasons, but from my perspective, I'm a junior PhD. I feel that it is kind of unlikely to get my paper in if I study some sort of series like you did. The reviewers may ask, why don't I conduct experiments on larger data sets with the transformers with some simpler models or with the big data? Furthermore, I think as said by other audience or other professors, the opposite side of the claims of the phenomena in neuroscience are also true. For example, if you say that we need a generator and a classifier that can play in a game theory manner, we can also say that we can also feel that one end-to-end model may work very well. So the opposite side of some of the claims may also be true. So it can also be challenged. And furthermore, I think some of the claims can also be easily criticized as overclaimed because some of the points may not hold true in other cases. So I think this is one reason why there are more and more engineers just competing in the computer vision. So what's your opinions on this phenomenon, and how to make some really great research like you, yeah, as a junior PhD, yeah.
Honestly, I don't know. I'm just a single person. I think there's yes, the community in the past 10 years, there were seeds that it did capture a lot of attention, right? It's become very popular. Certain practice methodology has been advanced in the field, right? Especially on the engineering side. As I said, right? If you study higher level, but the advance is really about the assisted intelligence, right? We figure out a way how to transfer our knowledge, our understanding, right, from the data to the machines and train the machines in that way. So I mean, if you're this may be true for industry, right? I mean, industry can even they can also make things even commercially available. There's a lot of usefulness to this. I mean, that's what engineering is all about. We build a system that is useful for people. And especially if the benefits overweight the cost, right? We will do that, right? the many AI systems can already make money if they can. That's true. But the point is that I'm trying to say is that for if you are interested in research and neuroscience or even the future of robotics or intelligent systems, you should think about what's lacking, right, as a researcher. What can you really make things much better? To me, I mean, even Yang or Kung or Doris were in this proposal, we're trying to think about is that, what's really missing? Even Yang Kung's recent position paper is that thinking about ahead of time, right? What is the current practice is really missing, right? How to make it autonomous, right? The path to autonomous intelligence, that was his position paper. The same with, our game, many of our theme here is also trying to do this. Those are the mechanisms could make better systems, as we say in robotics or in many other autonomous machines, truly transform the current practice to a different level. So that's actually something I think for research-wise, of course it's risky, of course, but it's more potentially high risk, high payoff, right? Can transform the current practice of engineering. We learn things from nature. As I said again, right? The current understanding, why it's very resource consuming, tremendous amount of data, training. That's exactly the lesson even control system people have learned about 100 years ago. Open loop control works. And if Wiener has not introduced feedback, we might have gigantic controllers, right? And to identify the system. I have a joke about this, right? How Google got to build an air conditioner, air conditioning control. You can collect the weather information for the past 10 years, 20 years, or the temperature of every place in your house, right? Boost into a neural networks. Learn a controller for your air conditioner. It will work. And you can even publish a science paper, so how wonderful that works. Millions of neurons, right? And it can control the temperature for the next 10 years if the weather doesn't change that much. But don't expect this to be cheap. Don't expect to be adaptive. Don't expect to be robust. Yet, the great success of Norbert Wiener by observing how nature controls things through closed loop, right? Now we have air conditioner in every room. Only one single thermometer is needed. You don't need a gigantic neural network to invert the air dynamics of your house to do that. That's a huge difference, right? There are very simple principles at work. As I said, again and again, right? There's a justice, maybe delayed, but never absent. Principles always work, right? Maybe delayed, but never absent. Probably has never been, just because we didn't know that. So that's actually separate. So those are really just for research-wise. I really hope the young generation will see, rather than just following what's really popular, right? Really see what's lacking in the current practice, because that might be your best opportunity to do something truly fundamental and truly transformative in the future. Yeah.
Yeah. Thanks for your advice, and I also think so. I also, from my experience, I also feel that keeping some simple principles in mind can work very well. Previously, I conducted a lot of research in reinforcement learning, and I found that many of the neural networks is simply not working. Rather, instead, if we develop some simple principles, they can work very well in the industry. And I also have another question. From your talk, I think it's very interesting to put your theory in my domain, and I think it also work very well, and your opinions are very inspiring. However, I just feel that from your talk, you I just can't find any theorems about the specific data structure, because I think a deep data understanding is very important from my experience, and I also think that if we need to develop a theory for the AI in the next 100 decades, not next 10 decades, we also need to have some sort of deep understanding in different data sets. For example, we all know that there are very deep understandings in classifiers, in classification models. However, we found that in different cases, in humans, in human pedestrian detection or segmentation, in different cases, we also need different kinds of models currently. So I don't know how to incorporate such a understanding of data into the theory of the first principle. Yeah.
Yeah, so so far the mathematics always a little bit behind, right? Because mathematics requires the rigorous proofs, right? So far I think I can tell you that for mixture of subspace or linear structures, low dimensional linear structures, the theory has been very much complete. And this is the book, and also even in our framework, right? In the game theoretical closed loop, the only theory we know that it's actually we only are able to prove things for the data structure is linear. Now, but yet the real data is never linear, right? So then what is the true distributions, and also what mathematical assumptions it holds, characteristic it holds? That's really just at the beginning, right? How to formulate the problem, the characteristic of the real distribution can characterize. Many of the model, right, people play with these days with, the statistical model actually very inadequate in this case, especially not allowed to do very rigorous analysis or guarantees. We're at a very early stage of this. Everything listed here, questions, we don't have rigorous justification yet. And it turns out, just give you a sense how hard those problems are, even for piecewise linear distributions, Gaussians, right? So the optimal solution to this object function happens to associate with this so-called Braskamp-Lib inequality. Terence Tao has quite a few papers about this about 10 years ago. This is called the mother of all inequalities. Basically, understanding the ratio of the whole and the parts when they achieve maximal or minimal is one of the hardest problems in mathematics, right? But nevertheless, I mean, I'm not saying that we have to solve those problems to be able to build useful systems to allow us to guide us to build useful algorithms, right? They're parallel, they help each other. But we start to believe that, start to see those are the phenomena, or those formulations start to connect very deeply with some of the fundamental phenomena in mathematics as well. But it needs to be understood. And on the other hand, the practice, just like Professor Huang says, right, the practice will not be limited by the current status of understanding mathematically. But we will be able to discover phenomena, maybe will allow us to understand what are the correct assumptions, statistical or mathematical properties of the kind of data we're dealing with. Those phenomena will help us to clarify those things. But certainly we don't have answers for them at this point. And we're also in the process of doing that. Actually, in fact, recently, Doris, we actually had a lot of conversation about those. We were putting together how do we, the visual data, even related to what Jeff has talked about, how those spatial temporal relationships, properties of the data can transform to certain characteristics of the manifolds we're dealing with. And those are still quite open question at this point. But again, this sets up very, a lot of open questions for future to study. For, if either you are a practitioner or you are care about algorithm, you do machine learning, or you care about the neuroscience. I do believe even some of the fundamental mathematical problem has a lot to do with even how maybe neuroscience, the nature is trying to explore it or try to implement or emulate.
Thank you, Professor Ma. I think we are out of the time today. Thank you for enthusiasm of Zeling Zhao. If our audiences have any questions, I think we can communicate via the email. Thank you very much today for everyone attending this event. And it's very late, the midnight in Beijing. And have a nice day and see you next time. Bye-bye.
Bye. Thank you.
Bye.
Thank you, everyone. Yeah. Bye.
Thank you, Professor Ma. Goodbye. Thank you, Professor Huang.
Bye,
Goodbye.
Karl. Yeah, bye.
Thank you, Professor Friston. Goodbye. Thank you, Professor Tsao. Goodbye.